Everyone, and welcome to this webinar session. It is a great pleasure for me today to welcome Cédric Gomez at this webinar session. Cédric currently works in the Department of Chemical Engineering at the University of Liège on a tenured researcher position from the Belgium Funds for Scientific Research. Trained as a physicist and a mechanical engineer, Cédric did a PhD in chemical engineering. Then he had several appointments and visiting positions in engineering, mathematics, and chemistry departments in Princeton, Leuven, Brisbane, Utrecht, and Jülich. His main research interests concern physicochemical phenomena occurring inside nanoporous solids in the broader context of adsorption, electrochemical, and catalytic processes. He is particularly interested in the modeling of disordered porous systems using stochastic methods and in experimental studies based on synchrotron and neutron scattering, in particular small angle scattering, and more recently, neutron spin echo. Cédric, please, the floor is yours.
Okay, thank you very much, Frédéric, for offering me to present to today. Really, I'm particularly grateful because I joined this cost action while it was already running. So I'm basically going to give you an overview of what I'm interested in, just as a way of introducing myself. As a minor detail, you might have noticed that I put in the chat a link to the PDF of the presentation in case you want to download it, if it's easier for further purposes. Yeah. So indeed, this is a presentation on small angle scattering in porous material. Of course, okay. Yeah. And that's basically the outline of my presentation. I'm just going to give some generalities about small angle scattering and nanoporous materials from the perspective of my interest. And then I advertise in the abstract just one of the examples, is the last one, capillary rise in mesoporous carbons. But I figured that if this is the purpose is to introduce myself, I also talk shortly about broader interests. So normally it's a total of 20 slides, so it should be over in 20 minutes, if that's any, if that's reassuring news. So porous materials, I mean, this is an action on porous materials, so we all know about them. But specifically, the type of materials that I'm interested in are those that are used in chemical industries and separation processes, typically. So I've highlighted this chemical plant here on the lower right corner, and perhaps something that people are not very used to, but when you look at the chemical plants like this from far away, 80% of what you're looking at has nothing to do with chemistry. It's about separation processes mostly, and in separation processes, porous materials are everywhere. And it's the physics, it basically boils down to the physics of absorption process, liquids in pores, and things like that. So the image here in the middle, this is a picture from the Jack Daniel's distillery in the 30s. So they are basically burning wood for producing charcoal, which is one porous material that is used in separation processes. Of course, I'm trying to, okay, yeah. So just to give you an idea of the type of things that I'm interested in, this is an example from a famous textbook to illustrate that the physical chemistry of liquids in pores is in nanopores is sometimes counterintuitive. So you all know that if you take water and if you put it in a bottle and you freeze it, because water, unlike most liquids, swells before freezing, the freezing is accompanied with the swelling of the material. And benzene, on the right here, so benzene, unlike water, shrinks when it freezes. Yeah? But these experiments are concerned with cement paste, which is nanoporous material with pore size typically ranging from 1 nanometer to 100 nanometers, and with the pores being filled with benzene. And what is plotted here is the linear strain as a function of temperature. So decreasing the temperature, so you initially see the material shrinking just because this is thermal contraction. Yeah? And the interesting thing is this part here, yeah? And this is basically, you see that the material swells macroscopically despite benzene itself shrinking. Yeah? And this is a typical phenomenon that you can only observe in disordered nanoporous material. I'm going to explain this here just as an illustration of things that I'm interested in. And this particular effect results from the combined effect of nanometer-sized pores and disordered structures. So the story is that the freezing temperature of liquids in pores depends on the pore size. And basically, the smaller the pores, the lower the freezing temperature. So if you cool this benzene in cement, progressively, you reach a point where you start to freeze benzene in the larger mesopores, but it remains liquid in the smaller pores. Right? And as a consequence of these larger pores benzene being frozen in larger pores, you have the chemical potential drops in these pores, and so the liquid from the other pores is being sucked in these larger pores. This is why you see this swelling macroscopically, despite the fact that benzene itself shrinks. You know? And of course, if you want to analyze these type of things, doing experiments in situ is extremely challenging because there are very few methods that you can actually use to study these type of phenomena. So I put here just a few experimental methods that one could use, and I've sorted them according to their resolution. So from macroscopic, so basically no resolution, and to nanometric, typically microscopy, electron microscopy, and the vertical scale is whether you're seeing like what I call collective behavior. Typically, you see phases as opposed to seeing molecules individually. So typically, in the upper right corner here, you have thermal effects. So you're cooling down and measuring the heat released when liquids crystallize and things like that. And then, if you want to do the same type of experiments, like with resolution, with spatial resolution, you could do visible light microscopy down to the micrometer range. But if you start to be interested in nanometer scale phenomena, basically, as soon as you're concerned with liquids or putting things inside pores, this rules out electron microscopy. And so there is very little you can do. And small angle scattering is one of the few things that you can do to analyze typically phases inside nanopores experimentally. Yes, so this is just taking some advantage of this to make some self-promotion. This is an educational paper we wrote about small angle scattering with German colleagues. And what you're seeing here on the left is two typical small angle scattering setups. So the one on the bottom is from the Belgian beamline at the ISRF in Grenoble, and the one on top is the Newton scattering beamline in Garching, operated by the Forschungszentrum Munich. So in both cases, the setup is the same. So you're sending an incident beam on the sample, and the experiment is essentially similar to X-ray diffraction, only you're measuring extremely small angles. So to some extent, small angle scattering is like analyzing the fine structure of what you might consider like the direct beam going through the sample in classical X-ray diffraction experiments. And if you want to resolve these very small angles, you have to put the detector very far from the sample. So that's why you have these long tubes in both configurations. And so this provides in the end extremely flexible environment to do experiments, because all you need is a way to prepare your sample, the experiments you want to do, and shine either X-ray or Newton beam through it, and then you can follow, in principle, what you are interested in. So, yes, the type of thing that you might want to analyze with small angle scattering, and I say eventually because this comes with some major challenges, but yeah, it's typically what would happen, for instance, in fuel cell electrodes, where so this would be like a porous, typically a porous carbon, because it has to be electrically conductive. So you have a pore that would be, say, 10 nanometers across. You have metallic nanoparticles used as catalysts. You have a proton conducting membrane that brings protons in, oxygen that flows in, and then typically this reactant creates water. And questions that you may want to ask is, where does the water condense, or does it stay in the vapor phase? And if it's condensed, well, that's interesting in the first place because it's capillary condensation. Then where does the water go? Does it plug the pores? Well, etc. And the major challenge addition to finding experimental setup that enables to shine X-rays through, is the data analysis. So yes, so this is all the mathematics of scattering data, small angle scattering data analysis just fit in these two equations there from a historical paper by the Bay. So basically, this boils down to saying that the scattered intensity is the Fourier transform of the electron density correlation function, and there is nothing else to it, right? And so I have this slide here that was that I prepared because further to a question that was asked by one of my daughters, who asked me what I was working on. So I managed to put it in a way that it was understandable by a 7-year-old. So don't feel offended if I'm presenting this. But so the way I put it is the following. So I told my daughter, well, you make a black and white drawing, and you hide it from me. And then you play the following trick. You take matches, yeah, and then you toss them randomly on your drawing. Yeah, for instance, that would be like one match, randomly matches would fall randomly on the drawing, that, and you count how many of these matches have both ends that fall in the black phase. Yeah. So in this case, it's not a single one because this is in, this is out. For instance, like if this match would count as well. You count this, and then you repeat the experiment with longer matches, okay, and then shorter matches, yeah? And then you give all these numbers to me, and based on these numbers, I try to guess what the drawing is. And so this is what is shown here. Yeah. So this is, for instance, like these matches here, these intermediate-sized matches. There would be like this point here, and then longer matches here, shorter matches here. So these black dots, this is the match tossing. So in technical term, this is a correlation function. Okay? And what I've shown here is just these random points, and in red, this is the correlation function from these random point configurations. But yeah, you can look for point configurations that actually match the correlation function. And this thing is running here is an approach called simulated annealing. The details don't really match. So basically, it's trying to find a configuration that has exactly that same correlation function. And you see now it's starting to converge. Yeah, but that convergence is relatively slow, so I'll just cut to the chase, and this is where it ends. Yeah? So you see, I've used here periodic boundary conditions. So basically, the cap that you see here actually belongs here, right? And also, these match tossing are completely blind to the orientation, right? And so this is why I have the structure. But the message here is that despite these seemingly a very indirect method, there is really a lot of structural information contained in these correlation functions, provided one can find a way to extract it. And yes, in her introduction, so Frédéric mentioned that I was very much interested in stochastic models. So this is the general context of these models. So they're just like these mathematical methods that one can use to reconstruct structures from correlation functions. Yeah. So I will not really enter into technical detail, and just now move to the second part of the presentation, just to illustrate how these can be used in porous materials. So the first example I talk about is the case of spatial distribution of nanoparticles in supported catalysts. So this is some work that I did a few years ago with colleagues from Utrecht. And so they were preparing a supported catalyst. So basically, you see these images here. Those are from electron tomography reconstructions, so 3D TM reconstructions. This was a mesoporous silica, or the mesoporous silica, you see pores here. So the scale is about 10 nanometers. And depending on how they prepare the catalyst, they managed to have a homogeneous distribution of these are copper nanoparticles inside the pores, homogeneous or more heterogeneous. And this spatial distribution had really important influence on the stability of these catalysts. But when you do microscopy, you're always characterizing an extremely small fraction of your sample. You can, so this thing here would be like 100 nanometers. And if you estimate the weight of an object like this is a femtogram. Yeah? So 10 minus 15 grams. Right? And you have to compare that with typically the ton, because that's the scale at which these materials are used in chemical processes. So if you just compare that, you know, the ratio is 10 to the 21. So basically it means like you have basically, you know, in a chemical reactor, you have about as many of these grains as you have water molecules in a dewdrop, right? So people are always obsessed about how representative these characterization is. And that's where small-angle scattering plays a role, because when you do small-angle scattering, you are characterizing a macroscopic amount of samples, say of the order of a few milligrams. Yeah? And this is a scattering pattern of these materials here. So you have these sharp, this is the scattered intensity as a function of this thing is basically proportional to the angle. So you have this sharp peak here, which comes from the fact that this has an ordered pore structure, but the information part, the information is in these background here. So these diffuse background characterizes the spatial distribution of the particles inside these pores. And to really capture this, we have to build a model so that accounted for the various structural levels in the porous material. So of course it has an ordered mesoporous structure, but inside, between neighboring mesopores, you also have micropores, and also have the mesopore does not extend forever, it's the form of grains, right? And then once you have these models for the porous material itself, then you can model the metal loading. And there we just had like just a one parameter model, basically telling you whether all the material is concentrated into a few pores or homogeneous distributed. And by doing that, in the end, you're able to quantitatively describe the scattering patterns just in terms of that single parameter that tells you is the active phase inside a few pores or homogeneously distributed. And in the end, so basically compared, if you combine these things with these small-angle scattering with 3D TEM, so of course it's quantitative now because we have a model, and the striking thing is it enhances the sampling by 12 orders of magnitude compared to microscopy. And of course, now you can also use that for doing in situ studies, typically seeing while the material is being used or while the material is being produced, how this nanoparticle evolves. The second example I want to show is the case of a liquid inside nanopores. So these are a bit academic experiments that we did with nitrobenzene and hexane solutions, which we put inside the carbon gels. So these are the type of materials, carbon burogels, the type of materials that are typically used in electrochemical applications because they're electrically conductive. And so we fill the pores with a solution of nitrobenzene and hexane. And so the interest of this solution is that it has a critical solution around 20 degrees. So basically, if you're above 20 degrees, so the two liquids are miscible, and if you cool it down, so the two liquids can't stand each other. So you know that you have these two liquids that can't stand each other, and yet they're bound to stay inside nanometer-sized cavities. But you know that interesting things are going to happen. And in principle, you know, they can do at least three different things. You can make layers. So one of the liquids would make a layer, or you can make plugs, or floating capsules. And it's unclear what will happen. And so this is what the small-angle scattering data look like in these systems. So that's the scattered intensity as a function of the angle, essentially, for different temperatures. And here is the wide-angle scattering. So this is measured at larger scale, larger angles. So basically, that's the diffraction that you're measuring diffraction. So you see that when you're cooling it down, you first see these small-angle scattering that goes all over places, and yet the liquids remain liquid. It's only at lower temperature that you start seeing these diffraction peaks that correspond correspond to the crystallization of the nitrobenzene. And interestingly, if you the area under these curves, right, is related to the volume of the scattering phases. So this area under these curves in the end is relatively constant, which means that all these things is just like the liquids are restructuring each other, restructuring, relocating each other inside the pores, but not changing in volume. So they're not dissolving. So in the end, using these stochastic methods that I just mentioned, so you can try to reconstruct the lid configuration of the liquid as a function of temperature. And this is what is done here. So here you have the scattering intensity. So see if the dots are the data, and then the red line is the scattering intensity of the reconstructed structures. Just for comparison, you see these dashed line here. This is what you expect in case the liquids would be completely mixed inside the pores. So there is a strong signal from these nanometer structure of the liquid. So gray is the solid, and then green is the hexane, and red is the nitrobenzene here. And what you're seeing actually is that the liquids, it's a de-wetting transition. So basically, at high temperature, so the nitrobenzene makes a nanometer thin layer that covers the surface more or less homogeneously. And when you're cooling it down below the critical temperature, you have these wetting transitions. So you see these bare patches of the solid that appear, and the liquid gathers into these floods there. What's happening there actually is that when you're moving away from the critical point, the surface energy of the hexane nitrobenzene interface increases, and this is what is driving this process here. Yeah, and the third example is the one that I advertised in the abstract. It's small angle scattering analysis of capillary rise in porous carbons. So those porous carbons. This is the structure of the porous carbon itself, the mesoporous structure of the porous carbon, reconstructed from small angle scattering. And actually, the porous carbon at smaller scale is microporous. So what you're seeing here is basically like that would be the small scale structure of what is shown here as the dense phase. Yeah? So really, you have these two families of pores, mesoporous and micropores. And when you do capillary rise experiments, so this porous that particular material which you're dipping in water and measuring the weight, you see water gets in, but it's mostly the large pores that contributes to the weight. And so the question is, where does the water go? You know, does the water enter the micropores at all? And for many applications, this is central because because most of the surface area is in the micropores. And so we did these experiments where we had basically the capillary rise experiment. So here is the porous carbon area. It's wrapped in aluminum foil to prevent side evaporation, and we are shining X-rays through it while the water is climbing up, yeah? And we're scanning up and down, up and down, up and down, yeah? Over a matter of about 1 hour. And what you're seeing here is not yet the small angular scattering patterns, but it's just the absorption. Right? Basically, we measure how many X-rays get through, and based on how many X-rays get through, we know how much water there is as a function of height for different times. Yeah? And the interesting thing is that you see we have these two-step process. So this sharp step here corresponds to the filling of the mesopores. So water arrives in the mesopores, but it's preceded with the diffuse step here, which is not completely clear what it is. Yeah? So, like it's kind of pre-wetting, and it's quite significant. You see, it's over like 1 centimeter, right? Over 1 centimeter ahead of the main wetting front, you still have water in some form. Right? And here is where small angle scattering comes in, because for each of these points, so basically for every position and every time, we have a full small angle scattering pattern. Yeah. So based on that, we can we can know where the water is. So to really, so what you're seeing here is the small angle scattering pattern at one height and for various times. So we're getting from red to grayish and then purple. Yeah? And so these are logarithmic scales. So really the signals are very strong. You see, you have a factor 10 increase and decrease of these things. So to really understand what happens there, you have to consider that the small angle scattering signal depends on the contrast between the phases. Yeah? So here, what I've sketched here is the micropore structure and the mesopore structure. And so at the micropore scale, so basically over here, the relevant contrast is between the carbon and whatever is in the micropores. Yeah? And at mesopore scale, the contrast is between these micropore skeleton and whatever is in the mesopore. Yeah? So when water gets in the micropores, so this, of course, decreases the contrast between the carbon and the micropores, and accordingly, this should decrease the scattering intensity up in the microporous region, and this is indeed what we see. And simultaneously, when water gets in the microporous skeleton, this should increase the contrast between the empty mesopores and the microporous skeleton, and this is also what we see. And then when water gets in the mesopores, then this decreases the scattering of the mesopores. So basically, what this shows is that this water enters the micropores, to the smaller pores, before entering the larger pores. And our understanding of what's going on there is actually it's the presence of water in the micropores that makes the mesopores hydrophilic at all. So this is a work that is done by like François Chaltin, who's working with me on this as a PhD student. So you see, this is in preparation. I don't know if François joined the presentation. But basically, I say it should be published in 2024. This is a thing that François should hurry up. Okay, so basically, yes, that's it. So I don't have any conclusion to that. It's just an overview of the type of thing that I do. So I really look forward to discussing any of these with you. And please, if this is of interest to you, please get in touch. Thank you.
Thank you very much, Cedric, for this very, very interesting presentation. It's really nice approach of how to probe the inside of the porous materials and get more interesting and challenging analysis and understanding. It's very nice. Do we have some question for Cedric? Okay. I will start with your very last the very last part of your presentation on this insertion of water in micropores prior to mesopores. I may have missed the information. Is it chemistry dependent on the material and its surface? I would say it's more the comparison I would make if you use a nitrogen adsorption, for instance. I am familiar with, depending on the affinity of the surface with the nitrogen molecule, then you will have a different covering of the surface with the nitrogen molecule, which is polarizable, and then even without filling the pores initially. So my question was, this result is transferable to any surface? That the presence of H2O in the micropores makes the mesopores hydrophilic?
Okay, so that's a different question. I mean, that's a different aspect. Yeah, the fact that it's water in the micropores that makes the mesopore hydrophilic. So we have so the wettability of these materials here is particularly critical for these specific materials, so these carbons, because they are used as, for instance, as supports in electrochemistry, and you really want water to go in the micropores because that's where the surface is. Yeah? So the surface area, most of the surface area is, and it yet it's really unclear uh, whether carbon by itself would be hydrophilic or hydrophobic. If you look at published contact angles, they typically are larger than 90 degrees. Yeah?
Yep.
And so on that ground, you wouldn't expect water to enter the micropores at all, right? And actually not to enter the mesopores at all, right? Uh, so, so this, in that respect, this question is specific to these materials, right?
Yeah.
So yeah, but so for instance, in other materials, for instance, in these mesoporous silicas, micro and mesoporous silicas, then it's really not. I mean, intuitively, when people would expect water to enter first the micropores and then the mesopores, right? Or taking the case of nitrogen, because nitrogen wets perfectly the surface of silica, then you also expect nitrogen to be first in the micropores and then in the mesopores. Like indeed you observe for nitrogen sorption at low pressure, you go in the micropores.
Yes. Yes.
So in that context, I mean, things are perhaps more intuitive than in the case of carbon.
Yeah. Yeah, the question was, do you other because you're on this carbon materials, but then the question is, do you have did you study other porous surfaces than carbon, and did you observe the same phenomena? Do you or
No, no.
it
I mean,
seems a very new approach that you describe, and
yeah. Yes, this is a PhD that is underway, and we started with these materials. Yeah,
sure,
because
because
but
it's interesting for application at the moment also.
yeah,
And
but I'm happy to discuss this.
yeah, because the affinity of the surface for anything that is entering, and in particular water, which is not the easiest. I mean, I'm a chemist, so that's why maybe I apologize for my questions that are very approximative. But the water to me is not the easiest molecule to infiltrate because it has a surface tension, and then it's a very interesting demonstration of how it goes into the pores and eventually condensate depending on the pore diameters. And also, I'm not familiar with carbon porous material, but that's why I would be curious to know how you can transfer this observation to any other material that are also very studied by chemists with their chemist vision of the affinity between the surface and the material. And and the other question then would be, it's very interesting with water and carbon in this case. Can you do the same with other molecule and see how they would infiltrate the pores?
Yeah, from the advantage of water from a physics perspective is that water is very simple. You have these. Basically, the experiments are just as simple as they get. You have just these water there in a petri dish, and then we're bringing the carbon on it, and there is the experiment. Yeah? So in principle, I mean, you could do that with any easy liquid. Yeah? But for instance, if you have things like liquid, you mentioned liquid nitrogen, that would be more tricky, right? But
Sure.
yeah, but if you have liquids, I don't know, organic solvents, provided they're not too volatile, maybe perhaps this type of experiment can be done. So, what type of system do you have in mind specifically?
Oh, I was just curious to just different liquid organic solvent could be because they have a different they are easiest to infiltrate, different surface tension, and I was wondering in the case also of pure materials that are pure liquids. I mean, for in the context of for drug encapsulation.
Oh, like that.
It's
Yeah.
it's a bit shifted to a different application, but I was curious of how to, because it's but they are usually in solution. But if it's a pure molecule, which is liquid, and it's a pure substance, I was curious to know when we switch to more organic thing, how it would behave and what it could bring in term, as insight in term of encapsulation and then release, because encapsulation is one aspect of the problem, but then what is interesting is the release profile and kinetics, usually when it's trapped into porous materials. But then it definitely depends on how it is trapped and where it is and in which state then it is, depending on the size. And I think this is a really interesting approach, but I'm not sure it's transferable to other application, but still it's very interesting.
The challenge with these drug encapsulation things, would perhaps be the contrast. Because here, the relevant contrast for the scattering signal is between water and nothing, basically. Right? And in the case of drug encapsulation, if you have, for instance, solutions, then I gather the relevant contrast would be between the water with drugs and the pure water. And that might be difficult to pick up in scattering experiments.
Right. Yeah.
But for instance, like some other experiments that we did, we still have to process them, was with so the same capillary guide experiments with electrolytes, so basically salt in there. So one of the questions that we were asking is, are the ions entering these micropores? Yes. And for instance, in these pre-wetting fronts there, are the ions there already?
Yes.
Or are ions coming later? But yes, that's things that we're currently working on.
Okay. Thank you, Cedric.
Yeah, you're welcome.
Do we have other questions? Yes? Ali Goli, please. Someone is raising his hand, I think. Yes.
Hello.
Hi.
Hi.
Thank you very much for your good presentation. I think that this investigation was done in the modeling and simulation base. Is it true? Only simulation
No.
or experimental?
This is experimental, yeah. But actually, it's both in different respects. The three examples I've shown. So it's experimental data. So these things that this slide here that you're seeing, these are the experiments. Yeah. So what is being done? You have these carbon here, and then that it's touching water, and water is climbing, and we're shining X-rays through them and measuring the scattering intensity as a function, when these capillary rise happen. So that's the experimental part. Yeah. And now you need the simulation, if you will, to convert these scattering data into structures. Yeah. So for the data analysis, you rely on models, but it's models for data analysis. So it's not simulation out of, say, first principles of physics, if you will. It's simulation to solve an inverse problem and reconstruct the structure from scattering data. Does that answer your question?
Yeah. I have another question. We work with console multiphysics. This software can be used for this porous material simulation, console multiphysics. Do you use anywhere?
I'm not using console, no. My understanding is that perhaps the type of simulation you have in mind is for example, so predicting these phenomena based on known surface energies, viscosities, physical characteristics. Is that the type of process that you have in mind?
We use the console for simulation of water splitting, hydrogen production by water splitting in the perovskite, in the electrode system, in the water splitting. I want to know, have you any idea to how can we can validate our experimental data with simulation data?
You know, I can only give you an answer of principle, you know, because of course it depends very much on your specific system. But so in principle you could. So what are the phases that you're creating? So what is your system specifically?
Yeah, we use electrolyzer, water splitting electrolyzer, and coated mixed metal oxide on the electrodes, on the surface of electrodes, and we want to predict or validate our data, our experimental data with theoretical or simulation-based data. I want to. You have any idea for this purpose?
But okay, so I can only answer for small angle scattering, for example. Yeah, with small angle scattering, what you see is a structure, right? So typically, if the structure changes, then you will see changes. You will see that in your data. Yeah? Typically, structure changing is like you're putting liquid inside micropores. That's something you can pick up, right? But now, if you have like chemical changes that don't change, you know, chemical processes going on that don't change the structure of the existing phases there, small angle scattering is perhaps not the best, not the best method to investigate this. But for instance, if you know, like you would create bubbles, you know, or locally replace your electrolyte with the gaseous phase at nanometer scale, this is something you might be able to pick up with small angle scattering.
Thank you very much.
I can only give very general answers, but yeah.
Thank you.
Yeah, you're welcome.
Okay, do we have more question for Cedric? I don't see any hand. Double check just in case. Okay, so we do not have more question. We can thank Cedric again for this very, very interesting presentation this morning. Thank you for participating again, and it was great. If you have a chance when it's published, I'd be happy to get the
Sure.
the
I'll
reference.
let you know. Yeah.
Thank you very much, and I wish you all a very nice day, and see you in a month.
Yeah, see you.
Have a good day.
Bye-bye.
Thank you again, Cedric, for your great presentation and participation. Bye-bye.
Thank you very much.
Bye.
Well done. Thanks.
Thank you. Thank you. Bye. Good luck.